So welcome back to our simulation. In this video, we're going to talk about how the program counter works. And I already have a video explaining how a program counter works, but we don't have this ability to jump to certain programs that we desire. So in this video, we're going to rebuild the program counter in order for it to have the ability to jump to whatever program that we desire. So that's exactly what we're going to do. So this is the main components of our program counter. If you remember, this JK flip-flop thing, clock signal goes in, and then we get this binary output because of these JK flip-flops. Okay, and then that went into this program counter, into this 4 to 16 bit, in order for us to pick what instruction set we want to be accessible via the bus. And now we're going to have this jump program counter. So this one's is a little more complicated. If you ever watch my transistor clock video, it works nearly the same way. So we have this register cell, this 4-bit register cell that goes into this half adder, because all we need to do is add the numbers by 1. But we want to be able to write whatever program. Right now we have 6 into this register. So 5 is being displayed out because it hasn't updated yet, but we can store whatever program set we want into this register. And that's what we can't do with the JK flip-flops, since there's no really storage ability onto it. And then this multiplexer right here tells us whether we want it to read the output of this little ALU circuit, or if we want it to read what it should jump to from the program counter and the opcode and the operand. And then we have the same 4 to 16 bit thing on the outside. So yeah, and this NOT gate makes sure that whatever is being outputted by the register is always added by 1. So every clock signal, we are increasing it by 1, just like a normal program counter. But if we want to go, let's say we want to go to program 12 with the jump signal on, it jumps straight up to 12. And then we can go back to really whatever one we desire. And we can use this via the opcode and the operand that we talked about in the control unit. So let's go to the CPU and we'll see how it works and flows with every other main component of it. So this is the CPU. So the jump signal is 5. So we're telling it to jump, and this opcode I made is a little confusing because when we tell it to jump, it's these 3 bits up here, and this bit determine what cell it needs to go to. This cell is a special cell that I'll explain later on, but that's how it's going to work. So if we have it jump, let's say we have it jump to 13. So when we go up, it jumps all the way up to 13, just like that. And then it's going to keep cycling through. So if we have it in clock mode, so it happens automatically, we can kind of see how it works. And then we can have it jump back to 1. Let me see. To 3. So this is going to come in handy, especially if we want to make a loop. So if we have, just like Arduino code or any other code, you have your void setup and then you have your void loop. And how does that work? It works with a jump function. So we can have a little void setup thing where we store certain numbers in the accumulator or in the register, and we only want to do it one time while the CPU is running. So we store them, and then we have a jump function. So instead of it looping all the way back around, it would loop just to where we want it to go. So let's say we have a jump function, the last one right here, right? Or I'm gonna let this thing reset so I can explain what I'm saying. Okay, so we're gonna have it jump all the way back to 4. So let's say the first 4 right here are stuff that we only want it to run one time and never again. So we let it run. It runs the first 4 stuff just like that, and then it's running all this extra stuff too. And then we have it loop back to 4. So we effectively made this forever loop, and we have this little void setup right here because it never runs again. And that's how it works on a logic gate level. So yeah, definitely a shorter video today because we already pretty much went through it, and it doesn't have anything that we don't understand yet. It is just 4 half adders, this little register thing that can store numbers and then add numbers by 1. So optimization, let's talk about that real quick. Again, it's really hard to optimize it. The only thing that I can think of is like we don't need this carry output for this half adder, so we can get rid of it right there. We only need the sum, which is an XOR gate, and making an XOR gate with transistors takes 7. So instead of these 4 NAND gates, which take 8, we can just put in an XOR gate to get the sum, and it would be a little more optimal like that by 1 transistor. Everything else requires, we've already kind of optimized it to the best of our ability. Especially since that this register isn't a clock register, it's just a normal register. And I already made a video with how do you make a register using bare transistors. And I think it takes about 7, maybe, I think it's 5. So yeah, but that's it for this video. I'll see you in the next one, where we are going to talk about the CPU as a whole. I'll see y'all then.